Okay, so today is our first day of the the logarithms and exponential functions unit. This is a unit that people can struggle with, especially if you are not careful with your algebra. So I'm going to say that right off the bat, just to try to get ahead of things. You need to be really careful in this unit about what are you allowed to do and what are you not allowed to do. One of the biggest problems I see is that people don't know what rules they're allowed to use in this unit, and because of that, they make up their own rules and do things they're not allowed to do. So these are the exponent law reviews you've learned in the past. And we kind of take a lot of them for granted. They're ingrained in our memory. We're going to learn some new rules this year for logs, and well, I guess new for people who are coming out of the 3U. And you need to be really careful about, how are those laws written and what does that mean you're allowed to do. So talking quickly about some of our exponent laws, if you multiply two things with the same base, you can add the exponents together. Only if they have the same base. It doesn't work if they don't have the same base. Same with division. Power of a product. So if you have something in brackets to an exponent, it's the same as taking the two things multiplied outside of the brackets. And applying that power individually to them. Same with the power of the quotient law. Oops. Here we go. Power of a power, an exponent, a power to another exponent. It's the same as multiplying those exponents together. Anything to the exponent of 0 gives you 1. The only time things would ever get messed up is if it was like 0 to the power of 0, which doesn't really make a whole lot of sense. But as long as that a is not 0, then you're okay. And so I'm going to add that actually onto this note right here, right now, and it will be on your printed version. So there, I've added it here. As long as a does not equal 0. Yeah, that one's true. So almost always. Newer, likely, are some negative exponents. So a negative exponent, it's the same as taking the reciprocal of your base and applying that exponent. Same if it's a fraction, you take the reciprocal and then the exponent becomes a positive. And then rational exponents, I think everybody has talked about last year. Let me know if this is not true. But if you have a fractional exponent, you can rewrite that as a root. So a to the power of, let's just going to focus, a to the power of m over n is the same as the nth root of a to the power of m, or you could write it with the exponent on the inside of the root, a to the m to the nth root. These mean the same thing. Sometimes it's our benefit to do the exponent first. Sometimes it's in our benefit to do the root first. Either way works. And one very common thing I see, let's say you have like a plus b squared or a plus b cubed, you can't just apply that exponent to those terms individually. You can if you're multiplying, you cannot when you're adding. So that's one of those things that I'm talking about where I often will see people make up rules, and that goes for exponential algebra as well as when we get into some of our logarithms. So we're going to look at a few different examples here. I'm going to switch over to paper and pencil because I don't have this note printed. I guess pen and pencil because it shows up better, but it will be laid out the same way as your note here. So the first question here, maybe let me do this so I don't get shadows. First question here is evaluate these exponential expressions if possible. One thing I noticed on the test yesterday is people don't pay attention to what these words mean. Evaluate, it means like write a single number. What is it equal to? So if you can, we're going to see what this is equal to. And if it's not possible, we're going to leave our answer with positive exponents. So positive exponents are always considered the simplified form of an exponential expression that can't be evaluated. Negative exponents in a final answer is not considered simplified. So you always want to make sure we turn the expression into something that has positive exponents. So 6 to the power of -1, we can use our negative exponent rule here. And so this is going to turn into 1/6 to the power of 1. So that negative exponent becomes a positive exponent. This, we take the reciprocal of it. And of course, 6 to the power of 1 is just 6. So this whole thing equals 1 to the power of 6. For part B, 2/3 to the power of -3. Again, we can use our negative exponent rule. This time we'll use the one that's written as a fraction here. There we go. So our negative exponent becomes a positive exponent if we flip it. So we'll flip 2/3. We get 3/2 to the power of +3. Now we have a fraction to an exponent. We can use this power of a quotient law and apply that power to both the top and the bottom. So 3 cubed over 2 cubed, and 3 cubed is 27, 2 cubed is 8, so we get 27 over 8. Part C, 2/3 to the -2. I've done this quite slowly to try to break up the steps, but 3 to the -2, same as we do with 6 to the -1, we can rewrite that as 1 over the 3 to the +2. And so then I've kind of rewritten this as a 2 divided by 1/3 squared, or 1/9. So that way we can see it's 2 divided by a fraction. If we remember fraction rules, you divide by a fraction, it's the same as multiplying by the reciprocal. So 2 times 9/1 is 18, or 18/1. So yeah, I've shown more steps than probably you might have to, but just to try to show how that's broken up here. This one here, 16 to the power of -3/2. We can use our rational exponent law. So a fractional exponent we can turn into the root to the exponent, or vice versa. But I've turned this into the square root of 16, because that's the second root, to the power of -3. Square root of 16 is 4. So 4 to the -3. Now negative exponents, as we talked about up above, we can turn that into 1 over our base to the power of the positive exponent. So 1/4 cubed. And then 4 cubed is 64. So we get 1/64, and we've evaluated that. So we've put it into simplest terms. For this one here, we have a fraction to the power of a negative exponent with the fraction in the exponent as well. So the first thing I did was I flipped the fraction to get a positive exponent. And then I used that fractional exponent, and I turned it into the roots. So the fourth root of 16 to the power of 81. And I'm just realizing I didn't include the exponent here. So now I have it fixed. Yes, the exponent from the 3, the base of this exponent was 4, so that's what type of root we have. And we can split up our root into the top and bottom and do the fourth root of 16, which is 2, and do the fourth root of 81, which is 3. So we get 2/3 all cubed. And as we talked about before, that's the same as applying that exponent to the top and the bottom. So 2 cubed is 8, 3 cubed is 27. That's our final answer. We can't simplify it any more than that. Last but not least, we have this question here, which is in a weird format. So one of the ways that can try to trick you, we got a mixed fraction. We have a decimal instead of a fraction. Well, 2 1/4 is the same as 9/4. 0.5 is the same as a fraction of 1/2. And then using our rational exponents, we can do the square root of 9/4, which just gives us positive 3/2. And so now that we've done some review of exponentials, we're going to start talking about logarithms. And you can think about logarithms in kind of the simplest form as a logarithm is trying to answer the question, what exponent do I need to raise one number to get a different number? And so we're going to look at a few different examples here. And so another way to think of that is how many times can you multiply one number by itself to get another number? So how many 2's do we need to multiply together to get 8? So we're going to look at both the exponential form and the logarithmic form. So 2 to the power of 3 equals 8. We're used to how we would read that out. And yeah, this means like 2 times 2 times 2 equals 8. Yeah, we would need 3 2's to multiply to get to 8. Whereas if we write that in its logarithmic equivalent form, we would write it like this with like a little tiny 2. Log 2, 8 equals 3. So we would say log base 2 of 8. And we call that 8 the argument. And maybe I'll write that in. I can't remember if I have this on the back, but this is the argument of the log, the base of the log. So log base 2 of 8 equals 3. And this is basically telling us that 2 to the power of what gives us 8. To what exponent do we need to raise one number to get to another number? Well, we would need to raise that 2 to a 3. 2 to the power of 3 gives us that 8. So these are very interchangeable. 2 is always the base. Well, no, I guess, sorry. For these examples, for both of them, the 2 is the base. The 3 is the exponent. So in a log, the exponent shows up all by itself. And that is going to equal 8. So yeah, 2 to the power of 3 gives us 8. And so writing this out in a general case for an exponential form, if we use these variables, a to the power of b equals x, and we wanted to try to write that in the equivalent logarithmic form, so that a is going to be the base, so we say log base a of our exponent of c equals b. So yeah, a to the power of what gives you c. That b is the part that would be missing when we use logs. Or I guess I should say when we calculate a log, it's going to give us an exponent. So expressing these answers into logarithmic form, we're going to do the same thing. Match up your base. So the base of this exponential is 7. The base of our logarithm is 7. Our I guess, answer to our exponential equation is now the argument of our logarithm, and our exponent in our exponential form is now what that whole log is equal to. So this is basically saying 7 to the power of what gives you 49? Well, 7 to the power of 2 would give us 49. 1 over 36 equals 6 to the negative 2. Same thing. Take the base of your exponential. That's going to be the base of our logarithm. What is this exponential equal to? That is the argument of our log. What's our exponent? We get negative 2. And this would be an equivalent form of this one here. Now, one more quick. Again, they've only asked us to convert. You don't have to do any you don't have to do any solving or simplify. We're just simply plugging this into a logarithmic form to get comfortable with it. So our base stays the same. 27 goes to the log, and the 3/2 can go on its own here. So now there's a few questions here going the opposite direction. You have a logarithmic form. Can we express our answers in exponential form? So here, yeah, same base of your log is the base of your exponential. This becomes your exponent. This argument is what's all by itself here. So yeah, that's saying 3 squared equals 9. With something a little bit more complicated. Again, your base to the exponent of what the whole log was equal to should equal 1 over 256. And yeah, that was just coming from original question. We can double check. Yeah, that makes sense. Like 1 over 4 to the power of 4. 4 to the power of 4 gives you 256. So that all looks like it identifies with what I had seen from people earlier. And then part C, log of 1000 equals 3. Well, here it's missing a base. So it looks like I can't really write anything in for my log. I should get rid of this equal sign because it's not really doing anything. And then we can kind of think, well, if there's no base here, what does that mean? Well, something cubed gives you 1000. Well, that would work if this number was a 10. And so that would make sense if this number was a 10. And so if we do not visibly see a base listed with the logarithm, like this one here, there's no base listed. This means the base of the logarithm is 10. So if you don't see any base, you just see log, that is a log with a base of 10. And so for example 5, we see that familiar word again, evaluate. It means like find the answer to these problems. The first one, log base 10 of 100, also could have written that as just log 100, means the same thing. But log base 10 of 100 is basically saying 10 to the power of what gives us 100. And so that, yeah, would equal 2, because 10 times 10 gives us 100. Now part B, I'll get written down here and I'll walk through an alternative method to look at this one. For the second part, log base 2 of 32, another thing you could think of is, well, I know this is asking me 2 to the power of what gives us 32. 32 we can rewrite as 2 to the power of 5, because that gives us 32. And well, this is saying this is saying 2 to the power of something gives us 2 to the power of 5. Well, that something, where'd we go here? Sorry. Yeah, 2 to the power of something gives us 32. That something has to be 5. The only way I can do 2 multiplied by itself and get 32 is I need to multiply the 5 by itself 5 different times. And then part C, so we can use some of that same information here. Log base 2 of 0.125. And 0.125, that's the same as 1 over 8. Now, so 2 to the power of something gives us 1 over 8. So we can try rewriting the 1 over 8 as an exponent of 2 as well. So 1 over 2 cubed. We can write that as 2 to the power of negative 3. So 2 to the power of something gives us 2 to the power of negative 3. Right, yes. And so, well, 2 to the power of something gives you 2 to the power of negative 3. So we can say this is just equal to negative 3. And so both of these examples, if we could get this base to match the base in our argument, just like we did here and here with 2 and 2, then that exponent is what the whole log is going to be equal to. Just like it was here. The exponent was 5, the whole log is equal to 5. And so 2 more examples here using that same idea. Rewrite the argument in terms of this base. So 2 is the same as the cube root of 8. So log base 8 of the cube root of 8 is equal to this. And then the cube root of 8, we can rewrite that as 8 to the power of 1/3. And so here again, we have those matching bases. It's basically saying 8 to the power of something is going to give us 8 to the power of 1/3. Well, yeah, that should be 1/3. That's the only way we can get 8 to the power of 1/3 is if that exponent is 1/3. Now this one as well, we have a fraction in our base of the logarithm, 27/8. We can turn that into 3/2 cubed. And so we want to get that same base here. I can flip my fraction, but it's going to turn that exponent negative. And so log of 2, basically 2/3 the power of something is going to give us 2/3 the power of -3. So that gives us -3 as the answer to that. And we're going to look at some more identities here on the back and come up with some ground rules for logs. And so we're going to look at some logarithmic identities here. I apologize if I'm a little kind of all over the, maybe not all over the place, but if I kind of trail off, I'm trying to record this in the different takes, and I'm doing this after everybody's gone to bed at home. So we've had to we've had to deal with a crying baby a little bit this evening. And so I am quite tired, so I may make some oral mistakes here as I kind of try to explain things, or even just maybe it's not super coherent at times. Let me know if there's any questions here. If I need to explain anything in more detail in person, and I'm happy to do that. So using some of the things we talked about on the back, really we want to rewrite this as the same base. Well, if these are the same number, 25 to the power of something gives us 25. Well, that's just going to be 1. Because really it's like there's an imaginary 1 right there. And then this base matches that base. Similarly, log 24 of 1, we could say that's the same as log 24. And well, 1, that's like the same as 24 to the power of 0. Because we talked about the 0 exponent on the back is always equal to 1, unless that base is 0 as well. And so we have a matching base and a matching base. This whole thing's just going to equal 0. Log base 5 of the cube root of 5. Well, the cube root of 5 we can rewrite as 5 to the power of 1/3. Our bases match, so that's just equal to 1/3. Now this one is a little bit weird looking, but this is basically saying 5 to the power of something gives us 125. Whatever that exponent was is going to equal this whole log. So whatever exponent you could put on 5 to give you 125 is going to be this log. And well, then that exponent, we're putting it on a 5, and we just said here that that's going to give us 125. So this part here again is saying 5 to the power of something is going to give you 125. Find out that something. And whatever that something is, we're putting it to the power of 5, which that we just found out, or we just talked about, that's going to give us 125. So something like this can just simplify to that log argument. So then we can kind of look in our general form a little bit here. If these two things match, just like they did here, this is always just going to equal 1. if we're doing the log base m of some number 1, just like we did here, that's always going to give us a answer of 0. And so we said that only doesn't work if the 24 doesn't equal 0. Well, of course, this is only going to work if m does not equal 0. And we're going to talk a little bit later on what some of these numbers and logs can be. But for now, yeah, we don't want that to be equal to 0. It wouldn't make sense. With a root or a radical or any sort of exponent, we've talked about, yeah, that's just going to equal whatever the exponent is. And similar to what we did here, this whole thing, like this whole thing equaled 125. This whole thing here is just going to equal x. So if you have m to the exponent of some log with the same base, it is just equal to whatever the argument of that log is. Most calculators, I should pull out a calculator here in just a moment. Most calculators are programmed to evaluate log with base 10. So we kind of talked about earlier, and I know I didn't quite write it in, but if you don't see visibly a base listed, that's going to use a base of 10 in this blank right here. And so calculators are the same way. They're used to doing logs with a base 10. If we want to use another base, we have to try to use this formula here. We call this the change of base formula. And so whatever your original log is with a base of b, you can rewrite that always as a log with a new base of a with your old argument x over your old base b as your two arguments of these new logs. So a is your new base. Generally, we want to use base 10 because that's going to let us use our calculator. And so we're going to see what this looks like in practice here in just a moment. I'm going to go grab a calculator. And so there's a couple examples here that say evaluate to 4 decimal places in example 6, these two logarithms. And so we're going to use this log here and our change of base formula to now sub in our base of 10 as our new base a. So let's see what that looks like in this example here. So argument goes on the top, 17. Base goes on the bottom, the 3. We have our new base, 10. Can be any new base as long as these bases are the same. But again, yeah, we usually use 10. And we also talked about writing a base of 10. You don't have to write that in. So log base 10 of 17, we can just say log 17. That base 10 is there. It's imaginary. Our default is base 10. So this is going to equal log 17 over log 3. And so your calculator likely has a log button, and we can do log 17 divided by log 3. And that's going to give us 2.5789. And so we'll write our answer in. This is approximately equal to 2.5789. I'll put in equals with a dot on top because this is approximate. I can do the same thing here with this second example. So this one here, log base 2 of 13, we can turn into log 13 divided by log 2, which equals approximately 3.7004 to 4 decimals. One thing I'll point out, yeah, this was how many times do we have to multiply 2 to get to 13, or 2 to the what exponent gives you 13? If you think about it, well, 2 squared is 4, and 2 cubed is 8, and 2 to the power of 4 is 16. So yeah, this is between 8 and 16, so it is between an exponent of 3 or an exponent of 4. 3 squared was 9. 3 to the power of 3 is going to be 27. Yeah, we get a number between 2 and 3 because this is between 9 and 27. So that kind of quickly checks out with what we would anticipate from those numbers. One more example here. This question here, example 7, create a single logarithm and evaluate. So we have log base 5 of 81 divided by log base 5 of 3. And we can kind of do the opposite thing we did here and turn this into a single logarithm where that's our argument and that's our base. Just like here, that was our argument, that was our base. Now that it's written like this, well, that's something we can solve on our own. We don't know what 5 to the power of what gives us 81, 5 to the power of what gives us 3, but we can think of it this way. 3 to the power of something gives us 81, and well, that something, 3 times 3 is 9, times another 3 is 27, times another 3 is 81. So this is the same as 3 to the power of 4, which means this whole thing is just going to equal 4. That's not obvious from looking at this, but we could double check. So log base 5 of 81 would be log 81 divided by log 5. And we're dividing by, so I'll put that in brackets, log base 5 of 3. So log 3 divided by log 5. So I have this whole big line here. Log 81 divided by log of 5 divided by log of 3 divided by log of 5, all in brackets. This should give us 4. Yeah, we get exactly 4. That's what we had here by doing it by hand. No calculator needed. That might be a hint going forward. Generally, we do a no calculator section on the logs test to really see, do you know your log rules? How confident are you with your log rules? So I'm going to say that now so that you think about that going forwards. You want to be able to do this algebra without the use of a calculator. Of course, this stuff you would need a calculator for. This stuff we don't. Okay, that is, I'm pretty sure, double check, that is the end of this lesson. So if there's any questions on this lesson at all, please let me know. I will be here tomorrow. I will be away for part of Thursday as well, as we have Turkey Bowl. So I'll make sure there's a similar video up for that. Keep giving me feedback on these videos and let me know if you think they're helping or if there's anything that you'd like to see changed, and I will keep trying to make sure that when I'm away, that impact is minimized. All right, so that's the end of this lesson. Keep me posted with how you're feeling, and let's keep going forward with logs. All right, bye.